Wait. Stop scrolling. Something is about to happen that's never happened before in human history. And it's happening in less than 5 days. NASA's Europa Clipper spacecraft, right now traveling toward Jupiter, is about to fly directly through the ion tail of 3IATLAS, that mysterious interstellar visitor we've been tracking, the one ranked 4th out of 10 on the Loeb Alien Detection Scale. Here's why this matters. For the first time ever, we're going to sample material from another star system. Not just observe it from millions of miles away. Actually fly through it. Collect particles. Analyze them. And here's the question nobody's asking publicly, but everyone's thinking. What if those particles reveal something we're not prepared for? I'm going to tell you everything. The dates, the science, the instruments, what they're looking for. And most importantly, what happens if they find something unexpected? Because between October 30th and November 6th, Europa Clipper will be immersed in a trail of charged particles that originated from a world we'll never visit, around a star we may never identify. Stay with me, because the implications of this are staggering. Let me start with the basics, but I promise we're going deep. 3IATLAS, as you know if you've watched my previous videos, is the 3rd confirmed interstellar object to pass through our solar system. It's currently hidden behind the Sun, approaching perihelion on October 29th. But here's what's new. As it gets closer to the Sun, it's doing something remarkable. It's releasing material. Lots of it. Water vapor, carbon dioxide, cyanide gas, nickel vapor, organic compounds. All of this is being blown away from the comet by solar wind, creating what's called an ion tail. Now, most people think of comet tails as those beautiful sweeping curves you see in photos. That's the dust tail, visible because sunlight reflects off tiny particles. But there's another tail, usually invisible to our eyes. The ion tail. It's made of charged particles, atoms and molecules that have been stripped of electrons by ultraviolet radiation from the Sun. These ions are then caught by the solar wind, that constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, and they're swept away in a nearly straight line. Here's where it gets interesting. Europa Clipper launched on October 14th, 2024, heading toward Jupiter. Its mission? Study Europa, that fascinating ice-covered moon that might have a liquid ocean beneath its frozen surface. An ocean that could potentially harbor life. But Europa Clipper's journey to Jupiter takes years. Right now, it's in interplanetary space, cruising through the inner solar system. And through an incredible coincidence, or perhaps fate, its trajectory is about to intersect with the ion tail of 3IATLAS. How did scientists figure this out? 2 researchers, Samuel Grant from the Finnish Meteorological Institute and Geraint Jones from the European Space Agency, they built something called Tailcatcher. It's a computer program that tracks solar wind. Think of the solar wind as packets of material constantly flowing outward from the Sun. Tailcatcher traces these packets backward, calculating where they've been. When a comet releases ions, those ions get picked up by solar wind packets. By knowing where the comet was and tracking the solar wind, you can predict where those cometary ions will end up. It's like tracking ocean currents to predict where debris from a shipwreck will wash ashore. Grant and Jones ran their calculations. They found something remarkable. Between October 30th and November 6th, 2025. That's 5 to 12 days from now. Europa Clipper will be in a region of space where solar wind packets that came close to 3IATLAS should be passing through. In other words, the spacecraft will be flying directly through the invisible ion tail of an interstellar comet. But wait, you might be thinking, isn't Europa Clipper millions of miles away from the comet itself? Yes, absolutely. The comet will be about 8 million kilometers from the central path that Europa Clipper follows. 8 million kilometers sounds like a huge distance. It is. But here's the thing about ion tails. They spread. Active comets like 3IATLAS, which is currently releasing tons of material per second, create ion tails that can extend for millions of kilometers. The ions scatter as they're carried by the turbulent solar wind. So even though Europa Clipper won't come anywhere near the comet's nucleus, it could still encounter particles that originated from that nucleus. Now here's the first big question. Is Europa Clipper even capable of detecting these particles? This is where it gets exciting. Europa Clipper wasn't designed to study comets. It was built to study Jupiter's moon. But, and this is crucial, it was built to study Jupiter's magnetic environment. Jupiter has an incredibly powerful magnetic field, and its radiation belts are intense. Europa orbits within that radiation, and scientists want to understand how Jupiter's magnetosphere affects Europa's potential ocean. So Europa Clipper is equipped with a plasma instrument and a magnetometer. These instruments measure charged particles and magnetic fields. Exactly what you'd need to detect cometary ions. The plasma instrument can identify different types of ions based on their mass and charge. Cometary ions are heavier than typical solar wind ions. Solar wind is mostly hydrogen and helium, very light elements. But cometary ions, we're talking about water ions, carbon dioxide ions, carbon monoxide ions, cyanide ions, and based on recent observations from the Keck telescope, nickel ions. These are much heavier. They have distinct signatures. If Europa Clipper flies through a region with elevated levels of these heavy ions, the instruments will detect it. The magnetometer, meanwhile, can detect something called magnetic draping. When the solar wind encounters a comet's coma, the magnetic field lines get distorted, creating a characteristic structure. If Europa Clipper passes through this distorted field, the magnetometer will record it. So the capability is there. The instruments can do it. But here's the problem. Does the Europa Clipper team know about this opportunity? And if they do, are they ready to act on it? Grant and Jones published their paper on October 15th. They've been trying to alert the mission team. But there's a complication. Timing. Europa Clipper is managed by NASA's Jet Propulsion Laboratory in California. JPL, like all NASA centers, has been dealing with budget constraints, government shutdowns, and internal restructuring. There's no confirmation yet that the Europa Clipper team has received the message or decided to activate the instruments during this window. And here's another wrinkle. Europa Clipper is currently in a phase of its mission where it's using its main high-gain antenna as a heat shield. It's close enough to the sun that thermal management is critical. It's communicating with Earth using a smaller medium-gain antenna, which means data transmission rates are slower. So even if the instruments collect data during the October 30th to November 6th window, we might not get that data back until weeks or even months later. But let's assume the best-case scenario. Let's assume Europa Clipper's instruments are active and collecting data. What could they find? Let's walk through the possibilities. Start with the most straightforward. The instruments detect elevated levels of heavy ions consistent with water, carbon dioxide, and carbon monoxide. They detect a subtle distortion in the magnetic field. This would confirm that Europa Clipper passed through the ion tail. It would be the first direct in situ sampling of an interstellar comet's material. That alone is historic. Scientists could analyze the isotopic ratios of these molecules. Isotopes are variations of elements with different numbers of neutrons. The ratio of different isotopes can tell you about the temperature and conditions when those molecules formed. For 3IATLAS, that means learning about the environment around a different star billions of years ago. They could also look for organic molecules. James Webb already detected organic compounds in 3IATLAS's coma. If Europa Clipper's plasma instrument is sensitive enough, it might detect ions from those organics, complex carbon-based molecules from another star system. That's profound. It tells us that the building blocks of life, or at least complex chemistry, exist throughout the galaxy. We're not unique. The chemistry that led to life on Earth isn't special to our solar system. But what if they find something unexpected? What if the ion composition doesn't match what spectroscopy predicted? What if there are elements or isotopic ratios that don't fit natural formation models? Now we're into speculative territory, but it's worth considering. Professor Avi Loeb has repeatedly emphasized that we should be open to surprising possibilities. If 3IATLAS were artificial, even partially, its outgassing might not be purely natural sublimation of ices. There could be controlled release of materials. There could be byproducts of whatever processes are happening inside. The ion composition might show patterns that don't match any known comet. I'm not saying that's what we'll find. I'm saying it's what we should look for. Science advances by considering possibilities and testing them. If the ions are perfectly consistent with natural comets, great. We've confirmed it's natural and learned about interstellar chemistry. If there are anomalies, then we have new questions to investigate. Either way, we gain knowledge. Now let's talk about the other spacecraft. There's a second opportunity here. ESA's Hera spacecraft, currently on its way to the binary asteroid Didymos and Dimorphos, will also pass through a region where 3IATLAS's ion tail might be. The window for Hera is October 25th to November 1st. That's today through next week. Hera is even closer in time. But here's the problem. Hera doesn't have the right instruments. It wasn't designed to study plasma or magnetic fields. It has cameras and spectrometers designed for asteroids. So even if Hera flies through the ion tail, it probably won't be able to detect it. An ESA spokesperson confirmed this, stating that because Hera lacks in situ instruments for measuring plasma, there's no real opportunity to study the comet's tail. It's frustrating, right? 2 spacecraft, 2 chances to sample an interstellar visitor, but only one has the right tools. And that one, Europa Clipper, might not even know to turn its instruments on at the right moment. This is the challenge of space exploration. Opportunities arise unexpectedly. We have spacecraft scattered throughout the solar system, but they're on specific missions with specific goals. Adapting them to unexpected opportunities requires communication, decision-making, time. and sometimes there's just not enough of any of those. But let's stay optimistic. Let's imagine Europa Clipper collects the data. Months later, after the information is transmitted back to Earth and analyzed, what do we learn? Here are some specific questions scientists are hoping to answer. First, what's the production rate of different molecules? How much water versus carbon dioxide versus carbon monoxide is 3IATLAS releasing? This tells us about its composition, which in turn tells us about the chemical environment where it formed. Second, are there elements we didn't expect? Spectroscopy from ground telescopes can only detect certain things. Direct sampling might reveal trace elements that don't show up in remote observations. Third, what's the size distribution of the ions? Are they mostly individual atoms and small molecules, or are there larger clusters? This affects how the comet's material evolves over time. Fourth, what's the temperature of the plasma? The ions carry kinetic energy. By measuring their velocities, you can infer the temperature of the gas when it left the comet. This gives clues about the processes driving the outgassing. And here's a big one. Are there any biomolecules? By biomolecules, I mean complex organic compounds that are associated with life. Amino acids, for instance. Or nucleobases, the building blocks of DNA and RNA. Now, I'm not suggesting 3IATLAS harbors life. But if the star system it came from ever had planets with life, and if some of that biological material ended up in comets, through asteroid impacts ejecting material into space, then theoretically, interstellar comets could carry traces of extinct biology from other worlds. It's a long shot, an incredibly long shot. But it's not impossible, and if Europa Clipper's instruments are sensitive enough, they might pick up signals of complex organics that are harder to explain through purely non-biological chemistry. Now, I need to address the question that's probably on your mind, the question everyone's thinking, but few are asking directly. Could this tell us if 3IATLAS is artificial? Let's be rigorous about this. If 3IATLAS were a spacecraft or probe, what would its ion tail tell us? Well, it depends on what it's doing. If it's using propulsion, burning fuel, or ejecting mass for thrust, the exhaust products would show up in the ion tail. But those products might not be dramatically different from natural outgassing. A probe using water as propellant, for example, heated by nuclear or solar energy, would release water vapor. That vapor ionizes in sunlight and gets swept into the tail. It would look like a comet. However, there might be subtle differences. The isotopic ratios might be off. If the water came from a different source than natural ice formed in that stellar system, the deuterium to hydrogen ratio might be unusual. Or there might be trace contaminants, metals, or rare elements that don't belong in a natural ice. Europa Clipper's plasma instrument might detect these anomalies. There's also the magnetic field signature. A natural comet's interaction with the solar wind creates a predictable magnetic draping structure. But if there were any active magnetic fields from the object itself, say from electrical systems or a magnetic shield, that could create additional distortions. Europa Clipper's magnetometer might pick that up. But here's the reality. The chance of detecting a smoking gun for artificial origin through this flyby is small. We're sampling ions millions of kilometers from the object. We're not doing a close flyby. We're not imagining it. We're catching a whiff of its exhaust. If there are anomalies, they'll be subtle. They'll require careful analysis, comparison with models, peer review, and even then, ambiguity will remain. Natural processes can produce surprising results. Proving something is artificial requires extraordinary evidence. A slightly unusual ion ratio isn't enough. So let's set realistic expectations. The most likely outcome is that Europa Clipper detects ions consistent with natural cometary outgassing. We learn about interstellar chemistry. We confirm 3IATLAS is releasing material rich in carbon dioxide and volatiles. We publish papers. We add to our understanding of comets beyond our solar system. That's a success. That's valuable science. But, and I think this is important, the very fact that we're doing this is significant. Think about what's happening. An object from another star system, potentially billions of years old, passes through our solar system. By sheer chance, a spacecraft we built happens to be in the right place at the right time to sample material from that object. This is serendipity on a cosmic scale. We're living in an era where we can do this, where we have instruments sensitive enough and spacecraft positioned throughout the solar system such that these opportunities arise. Dr. Michio Kaku often talks about humanity's transition from a Type 0 civilization to a Type 1 civilization on the Kardashev scale. Part of that transition involves expanding our reach into space, developing technologies that let us study and interact with our cosmic environment. This moment, Europa Clipper flying through 3IATLAS's ion tail, is a small but meaningful step in that direction. We're no longer just looking at the universe. We're touching it. We're sampling it. We're learning by direct interaction. And here's what excites me. This is just the beginning. 3IATLAS is the third interstellar object we've detected. The first, Oumuamua, was discovered as it was already leaving. We got a few glimpses, and then it was gone. The second, Borisov, we tracked for months and studied thoroughly. Now, 3IATLAS, we've had even more time with, and better instruments. We've got Hubble, Webb, Keck, Gemini, Mars orbiters, and now potentially Europa Clipper, all gathering data. Each interstellar visitor teaches us more. But here's the key point. These objects aren't rare. Based on detection rates and accounting for what we're missing due to observational limits, astronomers estimate there could be thousands of interstellar objects passing through the solar system at any given time. We just haven't detected most of them because they're small, dark, and moving fast. But our detection capabilities are improving. The Vera Rubin Observatory, coming online soon, will survey the entire visible sky every few nights. It's expected to detect dozens or even hundreds of interstellar objects per year. Within a decade, we'll have a catalog of these visitors. We'll start to understand their diversity, their compositions, their origins. And once we understand them better, we can start thinking about missions. Real missions. Not just lucky flybys, but dedicated spacecraft designed to intercept and study interstellar objects. ESA's Comet Interceptor mission is already being developed for exactly this purpose. It'll launch and wait in orbit, ready to be sent toward any promising interstellar visitor that comes through. Imagine a spacecraft that catches up to an object like 3IATLAS, matches its velocity, and rides alongside it for months, taking close-up images and samples. That's the future we're building toward. Which brings me back to the present moment. 5 days from now, October 30th, Europa Clipper enters the predicted zone of 3IATLAS's ion tail. For 7 days, it'll be in a region where cometary ions might be present. We don't know if the instruments will be active. We don't know if the data will be good enough. We don't know what, if anything, will be detected. But we know this is an opportunity. And in science, opportunities matter. You take every chance you get to learn something new. So what should we be watching for? If you're following this story, here's what to look for in the coming weeks and months. First, any announcements from NASA or JPL about Europa Clipper's status during late October and early November. If they mention activating instruments or special observations during this window, that's a good sign they're aware and acting on it. Second, look for papers from Samuel Grant, Geraint Jones, or the Europa Clipper team about this potential ion tail crossing. Even if data isn't immediately available, they might publish preliminary analyses or predictions. Third, watch for updates about 3IATLAS itself. Other observations, from JUICE in November or Juno in March, will provide context. The more we know about the comet's total activity and composition, the better we can interpret any data Europa Clipper collects. And finally, keep an eye on the broader discussion about interstellar objects. This isn't just about one comet. This is about opening a new field of study. Interstellar astronomy. The science of objects that travel between star systems. Right now, we're at the very beginning of this field. We have 3 confirmed objects and a handful of observations. But in 10 years, 20 years, we'll have catalogs, missions, detailed data. We'll understand how common these objects are, where they come from, what they're made of, how they formed. And maybe, just maybe, we'll find one that challenges everything we thought we knew. Because here's the thing. The universe is vast. There are hundreds of billions of stars in our galaxy alone. Trillions of planets. If even a tiny fraction of those systems produce technological civilizations, and if even a tiny fraction of those civilizations send probes or spacecraft into interstellar space, then the galaxy could be filled with artificial objects. Most would be inactive, dead, ancient relics from civilizations that rose and fell millions of years ago. But they'd still be out there, drifting through the void. And occasionally, one might pass through our solar system. How would we know? How would we distinguish an ancient alien probe from a natural rock? That's the question scientists like Avi Loeb are trying to answer. And the answer is, we look carefully. We gather data. We check for anomalies. We consider all possibilities. We don't assume everything is natural, but we don't assume anything is artificial either. We follow the evidence. 3IATLAS has 8 documented anomalies. Its trajectory, its early activity, its size and speed, its chemical composition, its structural integrity, its timing, its Oberth maneuver window. Each anomaly has natural explanations, but the combination is statistically unusual. It's ranked 4 out of 10 on the Loeb Scale. That doesn't mean it's artificial. It means it's worth investigating thoroughly. And that's exactly what's happening. International Asteroid Warning Network, NASA, ESA, observatories worldwide. They're all watching. They're gathering data. They're analyzing. And soon, Europa Clipper might add one more piece to the puzzle. So here's my conclusion. Whether Europa Clipper detects anything or not, whether the data reveals natural chemistry or surprising anomalies, this moment matters. We're witnessing the birth of a new era in astronomy, An era where we don't just observe distant objects. We interact with them. We sample them. We learn from direct contact. And with each interstellar visitor, we get closer to answering fundamental questions. Are we alone? Is life common in the universe? Have other civilizations explored the galaxy? Do artificial objects drift through space, waiting to be found? These aren't abstract philosophical questions anymore. They're scientific questions. Questions we can investigate with telescopes, spacecraft, instruments, data, analysis. And that's beautiful. That's what makes this moment in history so special. We're the first generation of humans with the technology to seriously search for evidence of other intelligences in the universe. Not by listening for radio signals, though we do that too, but by examining actual physical objects that come from other star systems. In 4 days, October 29th, 3IATLAS reaches perihelion. It'll be at its most active, releasing maximum material. And then, starting October 30th, Europa Clipper enters the zone where those released particles might be. For 1 week, humanity's most advanced interplanetary spacecraft will be flying through a trail of matter from another world. And we get to watch. We get to wait for the data. We get to see what science discovers. What do you think will happen? Will Europa Clipper detect the ions? Will the data reveal anything unexpected? Or will this be a near miss, an opportunity that could have been, but wasn't quite? Leave your predictions in the comments. I'll be following this story closely, and we'll post updates as information becomes available. Make sure you're subscribed with notifications on, because if something surprising happens, you'll want to know immediately. And remember, whether 3IATLAS is a comet or something more, whether Europa Clipper samples its tail or not, the simple fact that we can even attempt this is remarkable. We're explorers. We're scientists. We're a species reaching beyond our home world to touch the cosmos. And that's worth celebrating. Thank you for watching. See you in the next video with whatever updates we have. The universe is full of mysteries. And right now, one of those mysteries is about to give up a few of its secrets. Let's find out together what they are.